Hi, I want to talk to you today about Grover's search algorithm. This is next to Shor's factoring, the second most famous quantum algorithm. It is famous because it displays something we call quantum advantage, meaning that it is more efficient than any classical algorithm for the same problem. It was discovered in 1996 by Love Grover, and it was popularized by the tech media as a way of finding an element in an unordered list. In the classical world, with the computers we have today, to find such an element, we need to search every element of the list at least once. This means that our best algorithms today are order n, where n is the length of the list. But with quantum computers and Grover search, we can do that in order square root of n. This is a quadratic improvement. However, when transitioning from the classical world to the quantum world, there are some caveats. First, this is a probabilistic algorithm, meaning that it can give the solution with high probability, but not with certainty. The second is that in the quantum world, we deal with superpositions rather than lists. So Grover search is a way of finding a term in a superposition rather than an element in a classically defined list. Having this in mind, Grover search is now mostly regarded as a way of searching the space of all possible solutions to a problem for the single correct solution to that problem. That is way more powerful than finding something in a list. So how does it work? I will only give a bird's eye view of the structure now. We will go over it again in the implementation, but you can find a lot more information online. As with many quantum algorithms, we start by setting all our qubits in the full superposition. This is a uniform distribution across all the possible values. The second step is to apply an operation that will mark the states that we are searching for by flipping their sign, as you can see in the second image here. The third step is to apply a generic operator that will reflect all the elements across the mean value. The mean value is schematically represented here by this thin line. All the values that are above the mean will get reflected below it, and all the values that are lower than the mean will get reflected above it. You can see the result in this third image here. This will increase the probability of us measuring the search state. We now need to repeat steps 2 and 3 a number of times to further increase the probability of measuring our desired state. The number of times we need to repeat is given by this formula. Repeating more than this number of times will decrease the probability of measuring the desired state. So now let's pause and think about it. The first step is a simple one. We just need to apply a Hadamard on every qubit. The third step is a generic operator. It's called the diffusion operator. The only step that depends on the state you are searching for is the second step. We need to flip the sign of the states we are searching. This can be done in more than one way, but it is usually done using phase kickback. So what is phase kickback? This is the phenomenon that only manifests itself in quantum computing. Let's say we have an operator that is designed like this. We have a set of control qubits and a single target qubit. The target qubit has an X gate applied to it if and only if a certain condition is met on the control qubits. This is like a generalization of the controlled X gate. This condition can be anything. It can be a really simple condition like, is the state of these qubits the binary representation of the number 3? Or it can be a complex condition like, is this state a solution to a complicated problem? If we start with the target qubit in state 0, we can see here below what will happen. And we can start with the control qubits in a superposition of states that satisfy the condition or don't satisfy the condition. And what will happen is that this state of the control qubits will get entangled with the state of the target qubit, and the states that don't satisfy the condition will be correlated with state 0 in the target, and the ones that satisfy the condition will get correlated with state 1 in the target. What I've talked about here is called an oracle. Now, please pay attention because this next step is really important. If we set the state of the target qubit to a superposition that has a phase, like the minus state, which has the phase minus 0, minus 1. In this case, if we apply the same operator, the phase will get copied to the states that satisfy this condition and not to the states that don't satisfy this condition. You can see this expressed mathematically here. I will not go into details of why this happens, but you can find information online with people that explain it way better than me, and you can verify it mathematically yourself. The point is that this is exactly what we want for Grover search. We can use an ancilla qubit in the state minus and use an operator like this, an oracle like this, to mark only the states that we are searching for, that satisfy the condition. We mark these states with the condition in the oracle. So we can have really simple conditions, as I said before, like if we know the state that we are searching for, as we will see in the implementation, or in practice, we don't know what we're searching for. We don't know the exact state, but we know that it satisfies, that it is a solution to a problem. So by encoding the verification of the solution in this condition, we can get out from Grover's search solution to problems for which we don't know what is the state that represents the solution. This is really powerful. Remember that the characteristic of NP problems is that they have solutions that can be verifiable in polynomial time. Having explained all that, let's get on with our implementation. We will search the full space spanned by 4 qubits, which is from 0 to 15, or in binary from 0, 0, 0, 0 to 1, 1, 1, 1. And we want to find the value 11, which in binary is 1, 0, 1, 1. Here, I'm using a quantum computing platform called Uranium, which has its own incorporated simulator that runs in the browser. So as a full disclaimer, I will not run this on a real quantum computer, but on a simulator. The link to this is in the description. The first step is to set our useful qubits in the full superposition. The useful qubits are the first 4 qubits here, and I will set them all in the full superposition using Hadamard gates. In the probabilities pane, we see that this amounts to a uniform distribution across all possible values. We can also switch to see the state vector, and here we can see our the value we are searching for, which is 1011, and the next step would be to change its sign to minus. So just for illustrative purposes, I will use a control Z gate to do that. And I will set the proper controls in the proper states. And you can see that setting the control Z gate in this way changes the sign exactly as we want it. Now, we could go on with Grover search and it will work perfectly fine. But as I said earlier, this is not what we want to do in practice. In practice, we do not know what value we are searching for. It's the solution to a complex problem. So we will not use this Z gate, but we'll use an oracle and phase kickback. So what we do is we use the next qubit as an ancilla qubit and set it in the state minus. Now, this complicates a little bit our state vector and also includes another qubit in the probabilities. So to avoid this, to only measure our useful qubits, we set measurement gates on our useful qubits. Now we only measure our useful qubits, but the state vector is unchanged. So now let's apply the oracle. In the state we want it. So what the oracle does is, if our control state is in state 1, 0, 1, 1, it will flip the ancilla qubit. And now it's more difficult to see in the state vector, but you can see that for the state that starts with 1, 0, 1, 1, these amplitudes are flipped. So they have a changed sign. Now, probability spin, nothing changes. Now, what we want to do now is apply the third step, which is the diffusion operator. And this is a standard operator. It's made up of Hadamard gates, X gates, and the control Z. And it does not depend on the value we are searching for, but it depends only on the number of qubits, of useful qubits. So yeah, we just add the needed gates. One more. And this is the diffusion operator. And if we look at the probabilities, we can already see that the probability of measuring 11, 1, 0, 1, 1 is 47%. So it's increased. Now to increase the probability further, we need to replicate this three times, the steps 2 and 3. So we do that now. Now adding this pair of the oracle and diffusion operator has increased our probability of measuring our state, the search state, to 0.9, which is 90%. Now I said we need to do this 3 times. And now our probability is 96%, which is really, really good. If we would to add this pair, the oracle and the diffusion operator, another time, the probability will actually decrease. So basically, this is the full implementation of the Grover search algorithm, searching a space from 0 to 15 for the number 11. What we have used here as an oracle is something really simple. In practice, we would have a more complex oracle, maybe using some ancilla qubits, or I don't know, some more complex gates. But the basic idea of implementing Grover is the same. You just change your oracle to your desired form. You have the diffusion operator, which is something standard that only depends on the number of qubits, of useful qubits. And then you repeat that the number of times given by the formula. So that's it. I hope you enjoyed my explanation and implementation of Grover search. If you think I did something wrong, I could have explained it better, or maybe I got something really wrong, please drop it in the comments. Bye. See you next time.